This material energy balances video is about the open system energy balance. Last time we talked about the closed system energy balance. And recall, what determines whether or not a system is open or closed is whether or not material streams are crossing the boundaries. So in a closed stream, I don't have any streams flowing in or any streams flowing out, and the energy balance can be expressed with this equation. So moving on to the open system energy balance, let me just draw a little cartoon of what an open system would look like. It looks very familiar to the systems that we've been studying so far, where you have process units with arrows flowing into or out of them. So the fact that this process unit has a material flow in and a material flow out designates it as an open system. So what changes between the open system and the closed system? Really, the only thing that's different is that we can now talk about energy flow rates because we have a rate of energy coming in. So let's just draw, this is how I usually draw a heater. This is how I usually draw a stir bar or some kind of stirring, some type of moving parts that denotes some type of work. So instead of Q, heat will be referred to as Q dot. So this is a rate of heat. And this work is going to be shaft work. So work sub shaft, and that is to differentiate it from flow work, which is another type of work. So just as before, let's start by just considering the general balance equation. In plus gen minus out minus consumption. It's always a good place to start when considering any type of balance. We will start by assuming that the open system energy balance is at steady state. And energy can be neither generated nor consumed. And I made a mistake here. So even though we're at steady state, we're not going to cancel the accumulation term because of how we define the energy balance. In and out terms are, again, you can think of it as what's the energy coming in, right? So this stream is going to have some amount of kinetic energy coming in, some amount of potential energy coming in, some amount of internal energy coming in, and also it is going to have a certain amount of flow work. So I'm going to denote that as W sub FL. And that is because it is flowing. So a flowing stream, by definition, has deforming boundaries and therefore moving parts. And you can express the amount of work that the fluid does on its surroundings. So if you think about in a pipe, if I take like just a little packet of fluid that's moving, it is going to push the next little packet of fluid forward. And each one of these packets of fluid is going to be pushing the fluid in front of it. That's where the work comes from, this flow work. Similarly, all these streams have the same amount of energy out. So flow work out, kinetic energy out, potential energy out, and internal energy out. So just like before, we're going to say that the input minus the output is going to be the amount of work or heat transferred to the system. So Q plus W and that is equal to the accumulation, or you can think of that as the final minus initial, or here it'll be out minus in. So I'll write this as the sum of energy of stream J out minus the sum of energy of stream J in, where if you have multiple inlet streams, you would simply add these up, or several outlet streams, same thing. Work here is going to be subdivided then into two parts. I have shaft work and flow work, which is going to be separate. And I need a term for the flow work. So flow work can be defined in the following way. It is the pressure of the stream times the volumetric flow rate of the stream. Furthermore, I can define, this is a thermodynamic quantity, define enthalpy. This may be a term that you've heard of before. Enthalpy has the variable name of H. H is equal to U plus PV. This is a flash forward to your thermodynamics class where you'll learn about other types of energy like this. So enthalpy is even more of a intangible quantity than energy. So I spent the whole video talking about what is energy, and enthalpy is similarly kind of difficult to understand. This is not a correct interpretation, but it helps me think of what it actually is. I like to think of enthalpy as the internal energy of a flowing stream. So for open system energy balances, we'll be talking about enthalpy instead of internal energy. And in section 7.4 of your textbook, there's a long derivation here, and I'm not going to show the entire derivation, but I'm going to recommend that you read this book and read this derivation. But after you mathematically manipulate this equation up here, you can derive the closed system energy balance, which looks very similar to, you can derive the open system energy balance, which looks like the closed system energy balance. So for the open system energy balance at steady state, it is Q dot plus flow work is equal to delta EK plus delta EP, where all of these are now flow rates, plus delta H instead of delta U, where delta H also has a flow rate, a dot that signifies that there's a flow rate. And so this is the open system energy balance. Just highlighting a couple differences between the closed system energy balance. I guess I'll write that one right below just for clarity purposes. Q plus W is equal to delta EK plus delta EP plus delta U. So the first thing you have to do when solving an energy balance is determine whether or not you have an open system or a closed system, and then use the appropriate equation. Closed system energy balance. Okay, the first change, which I just addressed, is that in the open system energy balance, all energy terms are flow rates, or energy rates, or rate of transfer. So this dot, again, signifies that the unit of energy is divided by a unit of time. And that, again, reflects the fact that things are flowing into and out of the system, as opposed to being closed and confined without a flow in or out. The second difference is the difference between work and flow work between the open system and the closed system. And that is, again, because the work term from the closed system energy balance had to be differentiated between flow work and shaft work. This is a mistake. This should be shaft work there instead of flow work. The other difference is that in the closed system energy balance, I have a delta U, which is internal energy. And in the open system energy balance, I have an H, which is enthalpy. Where once again, enthalpy is defined as U plus PV. And effectively what's happening in the derivation that I did not show, but I encourage you to read, is that internal energy U is being combined with the flow work PV to make it into enthalpy. All right, so most systems, like I said, will have to be either determined to be open or closed, and then you would go forth from there with the appropriate energy balance. So to close out this video, I wanted to talk about a quick practice problem. This is 7.21 in your book that says air is heated from 25C to 140C prior to entering a combustion furnace. The change in specific enthalpy associated with this transition is 3,349 joules per mole. The flow rate of air at the heater outlet is 1.65 meters cubed per minute, and the air pressure is 122 kilopascals absolute. Calculate the heat requirement, assuming ideal gas behavior, and that kinetic and potential energy changes from the heater inlet to the heater outlet are negligible. So once again, we'll not always see this, but we will commonly see this, that we will assume that kinetic and potential energy changes are zero. We won't always assume this. Sometimes we'll have to calculate it, but this can greatly simplify the calculation. Okay, so let's draw ourselves a picture before we talk about how to solve. I've got a heater, and I have air flowing in at 25C and air flowing out at 140C. We have a change in specific enthalpy. So the change in specific enthalpy in math terms is delta H hat. is 3349 joules per mole. So once again, the book does this weird notation where I would call this H underbar, but the book calls it H hat. I'm going to keep with what the book does for now, at the risk of being confusing. But just note that in future courses, specific molar enthalpy and specific mass enthalpy will be differentiated with notation. All right, what else do we have here? We have the flow rate of air at the heater. So we have an extensive variable. Therefore, we cannot set a basis. I have a volumetric flow rate, and I have a pressure, 122 kPa. So given that I have a volumetric flow rate, a temperature, and a pressure for the outlet stream, I can use the ideal gas law, and the problem tells me to assume ideal gas behavior in order to figure out what the flow rate of the exit stream is. So the first step to this is an energy balance problem, by the way, because it's in chapter 7, but even if it wasn't, anytime when I'm asked to calculate what the heat requirement is, and I haven't drawn in that on the diagram, for a heater, I like to draw a little heating coil, and that is the last variable. This is not a complete diagram, by the way, too. Remember, I need the molar amount and composition of everything. For the composition, it's just air, so it's going to be 100% air all the time. But my material balances, I need the molar flow rates. So in determining the amount of unknowns that I have in this problem, so doing a degree of freedom analysis, as I should always do, I have 1, 2, 3 unknowns, N1, N2, and Q. I can't set a basis because you might think because I don't know what the molar flow rate is, I can set a basis, but that's not true. I do have a basis set. It's just in terms of the volumetric flow rate there. So I'm going to use the ideal gas law. That's going to be one of my equations to calculate the molar flow rate of N2. Then I'm going to use my material balance to say that N2 is equal to N1. And then I'm going to use my energy balance to calculate Q. So that is how I'd lay out my degree of freedom analysis. So the first thing I would do is do, like I said, first, the ideal gas law. N2 is equal to PV over, nope, I got that backwards. RT, no, I had that correct. I had that correct the first time. PV over RT, where P is 122,000 pascals. Volumetric flow rate is 1.65 meters cubed per minute. R is 8.314, and T is 140 C. So I'm going to skip the calculations and leave the calculations for you. So you can calculate this flow rate. Remember, once again, I've made a mistake very deliberately here. I'm trying to get you to the point where you can identify mistakes that I make. So look at this equation, and you should be screaming into your computer monitors right now, telling me that I've made a mistake here. So once again, I'm going to allow you to calculate N2 on your own. And I'm going to make a little note that I made a deliberate mistake here. And I will expect you to figure out what it is. Okay, but it's not a mistake with the actual thought process. The thought process is still the same, where I'm using the ideal gas law to calculate what N2 is. I'm just saying don't plug these numbers into your calculator and expect that that is the correct N2. The second step would be to say that N1 is equal to N2 by material balance. And the third step, which is why this is a chapter 7 problem, is to perform an energy balance. And that's why we're here. That's why I chose this specific problem. So I need an energy balance on a closed or open system. I have air flowing in and flowing out, so I need the open system energy balance. Open system. So I'm going to take that equation, W shaft plus Q is equal to delta EK plus delta EP plus delta H. And problem says kinetic and potential energy changes are negligible. And I also don't have any shaft work. So when I say shaft work, I mean something being stirred or some type of work being derived if this is a turbine or something, but it's not. So there's no shaft work. And my energy balance reduces to simply Q is equal to delta H. And delta H dot is an extensive variable because it depends on the size. So in order to make it intensive, what I can do is pull out the molar flow rate. So make it N dot and delta H hat. Right, and the problem gives me what delta H hat is. It gives me that delta H hat is 3349 joules per mole. And I also have what the flow rate is. I have N1 and N2. So therefore I can say this is equal to N1 or N2, either would be the same, times 3349 joules per mole. N1, by the way, is going to be in moles per minute. So keeping my units so I don't get confused, moles are going to cancel and I'll be left with a Q that is joules per minute. So that was the point of the problem that it wanted me to calculate. What is the heat requirement in kilowatts? Oh, actually, no, I don't have that. So I'm going to be left with joules per minute. In order to calculate, to convert it to kilowatts, I'm going to have to convert minutes to seconds. So if I say 1 minute divided by 60 seconds, then I'd be left with Q in joules per second, which is equal to watts. So then the last conversion to make it kilowatts would then be to, of course, divide by 1,000 to make it kilowatts. Okay, let's briefly talk about part B. Would the value of kinetic energy, the change in kinetic energy, which was neglected, be positive or negative, or would you need more information to tell? If the latter, what additional information would be needed? So think about, what does kinetic energy depend on? Remember, kinetic energy is 1/2 m velocity squared. And because the molar flow rate is the same and I don't have any reaction, the mass flow rate is also going to be the same. So my mass flow rate between stream 1 and stream 2 is going to be equal. But what about the velocity? Will the velocity increase or decrease? And in this case, I don't know, so I won't be able to tell. So what additional information would be needed? I would need to know the diameter of the pipe or the cross-sectional area of the pipe so that I could determine what the velocity would be. So I have a mass flow rate. I could calculate what the density is. I would also probably need to know what the pressure is if I wanted to calculate the volumetric flow rate. Right, so all those things would be needed in order to determine whether or not the kinetic energy is positive or negative. So that'll do it for this video. Hope you enjoyed watching. See you on the next video.